Here's problem 3023. Each of two long straight parallel wires, separated by a distance of 16 centimeters, carries a current of 20 amps in the same direction. What is the magnitude of the resulting magnetic field at a point that is 10 centimeters from each wire? Alright, so let's imagine what's going on here. Let's straddle our two wires across the x-axis, and so we'll put one down here at x equal minus 8. And we'll have the current coming out of the board. So, and then we have another current up here at y equal plus 8. And since it's in the same direction, that current will also be coming out of the board. So we'll call this I1 20 amps, and I2 also is 20 amps. And we want to find the magnetic field at a point that is 10 centimeters from each wire. So it can't be directly in between these two wires. It's going to have to be kind of offset, kind of in this direction, in order for the distance to be 10 centimeters from one wire and 10 centimeters from the other wire. Which means, since we're looking at a right triangle here, hypotenuse being 10, one side being 8, that this other side must be 6 centimeters. It's a 3, 4, 5 triangle. Alright, so we want to find the magnetic field at point P. Now, employing the right-hand rule on I1, if I were to point my thumb in the direction of that current, which is coming out of the page, then my magnetic field would be going in a circle counterclockwise around this current, kind of like this. So at point P, we're going to have a magnetic field that is perpendicular on this circle, tangent on the circle, if you will. And let's call that magnetic field B1. It's coming out like that. And similarly, I'm going to have a magnetic field due to right-hand rule that's going counterclockwise around current number 2. And at point P, it's going to be tangent to the circle. And let's call that B2, coming off like that. The magnitude of these two fields will be the same. In other words, the magnitude of B1 will equal B2 is going to equal mu naught I over 2 pi r for a long straight wire. That is 4 pi times 10 to the minus 7 for mu naught. Our current is 20 amps, and we are a distance of 10 centimeters from each wire. So that is going to give us, let's see, I'll do this. So I'm going to have 40 times 10 to the minus 7, which would be 4 times 10 to the minus 6, divided by 0.1, which would give me 4 times 10 to the minus 5 Tesla for each of those magnetic fields. Okay, now we have a problem. We have to add these fields vectorially, and one's going off to the right and one's going off to the left. And we need to know what their components are. So we're going to have to do a little bit of geometry here. If I say that this angle here is theta, that would make this angle theta here. And I'm going to say its complementary angle in this 3, 4, 5 triangle is alpha. So that will be alpha there, and this whole thing over here will be alpha. Alright, but if I'm looking at just this right angle right here, then the complementary angle to alpha would be this short angle here, and that should be theta. So I have a theta there. I'm sorry. And so the angle that we're talking about for B2 with respect to the x-axis is actually theta. Let's look at B1. We have a right angle here, and we have alpha, which is the angle here. So we have alpha plus 9 degrees, and what's left over is this little angle over here to make 180 degrees all the way around. And that means that this must be the complementary angle of alpha, which makes this angle theta as well. So if you follow what my argument is, our thetas are going to be the angles that these two vectors are making with the x-axis. Okay, good to know. Now if I were to write these as vectors, I would have that b1 is equal to the magnitude b cosine theta in the I direction, let's make this a vector, plus b sine theta in the j direction. All right? So as we see it, it's going to be b times cosine of theta. We're looking at a 3, 4, 5 triangle, and theta is this angle here, and that's going to be 8 over 10, so the cosine of theta is 4/5, and the sine of theta is going to be 3/5. Alright, so there's my b1. b2 is going to equal the magnitude b, and it's going to be a negative cosine theta because we're going in the negative I direction, and then plus b sine theta in the j direction. So this is going to equal a negative 4/5 b I plus 3/5 b j. So if I add these two magnetic fields together, b1 plus b2, I'm going to get 4/5 b I plus 3/5 bj plus a negative 4/5 bi plus 3/5 bj. The 4/5 bi and the negative 4/5 bi cancel out, and so I'm going to have 3/5 plus 3/5, which will give me 6/5 b in the j direction. If we calculate what that is, 6/5 is 1.2. B we already determined to be 4 times 10 to the minus 5. And then all this would be in the j direction. So 4 times 1.2 will give me 4.8 times 10 to the minus 5 Tesla in the j direction. As we're looking at it on the diagram, it looks something like this. I have a x component of b1 that's going off like this. That's being balanced in the negative x direction by the same component. So those are canceling out. So I'm left with a b1y component that's going up plus another b2y component that's also going up. And those add together give me my net vector in the j direction. So our magnetic field is actually going in the j direction. It is 4.8 times 10 to the minus 5 Tesla, or 48 microtesla in the j direction.